Let me start. So the title of the talk is Local Statistics, Semidefinite Programming, and Community Detection. Let me start right away with the community detection. So let me define the stochastic block model. So in a stochastic block model with two communities, parameterized by P and epsilon here, you sample a graph as follows. You partition the set of vertices into two sets of half the size randomly, and you sample edge within each cluster with probability P times 1 plus epsilon over n, and across the clusters with probability P times 1 minus epsilon over n, each edge independently. So this is just a random graph model. And the goal is you receive this graph sampled from this model, and you'd want to recover the partition even partially from this graph. Now, let me define a weaker problem than recovering the partition, which is the distinguishing problem. Here, you're just given a graph which is either sampled from a stochastic block model that I described earlier, or you're given a completely random graph from the Erdős-Rényi model with the same average degree. So you have a random graph where every edge is sampled with probability P over n. And you can check the average degree is the same. And so you're given one of these two graphs, and you'd like to know, you would want an algorithm that can tell which it is. So what is known about the problem of community detection with two communities? Well, if I plot the what happens to the problem with increasing epsilon, there is a threshold called the Keston-Stigam threshold. This is roughly epsilon is 1 over square root p. Exactly, epsilon is 1 over square root p, below which the problem is information theoretically impossible, and above which efficient algorithms exist to solve the problem. And now there are a few different versions of the efficient algorithm for this problem, using path counting and various other things. But one simple version would be the second eigenvalue of the non-backtracking walk matrix. That's an algorithm to distinguish between a random graph and a graph sampled from an SBM. Okay, and what is the non-backtracking walk matrix? It's a matrix whose dimensions is equal to the number of edges, twice the number of edges. So you have one row and column for every edge directed both ways, and you have a edge you have a 1 when you have an entry UV, a directed edge UV to a directed edge VW. We'll see more about the non-backtracking walks matrix a little bit later, but it's the key point I want to emphasize. It's an asymmetric matrix, and this algorithm says you calculate its eigenvalues, which are complex numbers, and in case of a random graph, all of these eigenvalues, all of the non-trivial eigenvalues, lie inside a circle of certain radius, whereas in a stochastic block model, they'll be at one eigenvalue outside. Okay, so I did not put in any natural points to stop for questions in this talk. So please stop me if there are any questions at any point during the talk. Okay. So now let's look at SBM with K communities, and here the model is the same. You divide the graph into K communities, and between clusters there's some probability B over n, and within clusters there's some probability A over n of adding the edges. So what's known about K communities? K communities, actually the picture becomes more complicated. So there's some parameter, let's say, which is like the signal to noise ratio. I'm going to plot it as epsilon here. And as again, there's a Keston-Stigam threshold. Above the K, and there's above the K's threshold, we know that there is efficient algorithms to solve the distinguishing problem. And then there's a point below which the problem is information theoretically impossible, as in the two distributions are information theoretically indistinguishable from one another. But there is a region of the parameters where the problem is information theoretically possible, but conjectured to be computationally hard. And this happens as soon as the number of communities k is more than 2. There is a region where the problem is supposedly computationally intractable. And again, the second eigenvalue of the non-backtracking walk matrix is a distinguisher for this problem. And our, one starting point for our work, you could ask, okay, can we use SDPs to solve this problem of community detection? Okay. And then why would you want to use SDPs? There are a few different reasons. Firstly, it's a systematic and unifying algorithmic technique. Secondly, the issue is about robustness. So let me talk about robustness. So we have this distinguishing problem where a graph is sampled exactly from some distribution, and we want to distinguish the two cases. But imagine if an adversary arbitrarily corrupted delta and fraction of the edges in the input graph. And this is just in some sense deviation from the model. We have a probabilistic model for the graph, and how robust is your algorithm to actually some small deviations from it? Well, it's not clear how the algorithmic landscape changes once you add in this ingredient of robustness. In particular, we don't know the following fact. We didn't know this following fact before this work, is that suppose I make delta go to zeros, meaning the adversary corrupts little of n edges. Does the threshold stay the same? So if the adversary only corrupts n over log n edges, we should expect that the threshold stays the same. And is that true? And there has been some evidence that this case threshold is robust, but there's some other kind of evidence which suggests that it's not robust. So it was unclear. And one advantage of SDP-based algorithms, they are kind of naturally robust to small perturbations in input. We'll come back to this later. But I guess for me, the other more interesting reason why SDPs, one should study community detection and these problems using SDPs, is to study computational phase transitions. So let me go back to the picture we had. So this is the conjectured landscape for the SBM problem with K communities. So you have a Keston-Seagram threshold above which the algorithms exist, and there's a whole region where its problem is computationally hard. But how does one verify this extremely precise prediction of a computational phase transition? If there's a particular point which is very nicely predicted, below which the problem is supposed to become computationally intractable, and how does one verify this? It's a very natural question because there's also a very, very natural, easy to sample average case hard problem. If it is indeed hard just below the case threshold, it's an extremely simple average case hard problem that you might be able to sample and maybe even use for cryptography and things like that. So it's a very natural question whether this conjecture really holds water and is it true. And this is just one of a whole bunch of predictions which come out of the general toolbox of statistical physics. So the idea is they have canonical algorithms like belief propagation and message passing, approximate message passing, and some heuristic calculations on when those algorithms are fail and give you these predictions. So this is just one prediction for community detection, but there's a whole range of predictions which are very, very precisely laid out. So just to sort of show you some picture of how precise and intricate these predictions are, this is for the problem of low rank matrix recovery with some noise. You can see that there are precise regions of parameter space which have been mapped out as saying it's the problem is tractable here, whereas the problem is hard here, and so on and so forth. And this is just one problem, and there are lots of these predictions. And another example is refutation, right? So if you look at random, regular, not all equal SAT, the formula is satisfiable at a very low clause density. At a very high clause density, the formula is unsatisfiable, and it can be certified that it's unsatisfiable. And then there's a region where we don't know, and there's a kind of a prediction of as to where the problem should become hard. And so, how do we verify these computational phase transitions? Essentially, yes.
Can I ask a question?
Yes.
Is there some developed theory of reductions between the type of problems you are talking about, like computational phase transition problems? There are many of them, there are exact predictions, but do we know that if one is true, the other is true? Or,
yes. No, that's fascinating question. We don't know many reductions in this world. To my knowledge, there is some work on reductions for problems inspired from for average case problems. Like there are some reductions from planted clique to sparse PCA and things like that. But there's still no known reductions between these things. In particular, one really amazing thing would be to assume that, for example, community detection is hard at some regime, some qualitative regime, and prove that if it's hard in that qualitative regime, actually quantitatively some hardness amplification makes it hard at the threshold. Right? We don't know. Yeah, reductions are a great thing. We don't know that yet. Yeah, and so that was actually my point. Somehow is that, as of now, we don't know how to do it. We don't have many reductions between these problems. Partly because we want to map the distribution as we do the reduction, and that becomes a little bit tricky. So one, since we don't have a way to talk about computational complexity, we'll talk about something simpler. I guess the sum of squares degree, right? We could talk about whether the complexity of the problem as measured by the sum of squares degree, which is of refutation, or sum of squares degree of certification, whether that parameter changes as you cross this phase transition. And there is some partial evidence for this sort of hardness of these average case problems that can be obtained through sum of squares, which is already, for example, planted clique. We know log n rounds of Lasser would not solve it. But another example is random k-sat, right? So if you look at the number of clauses, with the number of clauses, there's a regime where the formula is satisfiable. Then there's a vast regime where going from some constant times n to roughly n to the k/2 clauses, where we don't know an algorithm, and beyond n to the k/2 we know a spectral algorithm. And there's somewhat of an empirical hypothesis that as the random k-sat should be hardest at the threshold, and it should get easier and easier as you add more clauses. And these things are sort of confirmed if you look at the SOS degree. If you look at the SOS degree, now we know, we know upper and lower bounds on the SOS degree that kind of nicely interpolate between the threshold of satisfiability to the threshold at which we can do refutation efficiently. But note that this transition is actually not as sharp as the community detection threshold, because the parameter ranges from n to n to the k/2, and then the complexity of the problem drops slowly. It could potentially be that for community detection at the case threshold, above the case threshold, it's a polynomial time, and below the case threshold, it's sub-exponential time. And that will be very nice to show. Okay, but then, so now we want to carry out this program of understanding this phase transition through SDPs. We immediately hit a bottleneck, is that we don't know of an SDP relaxation that actually achieves the threshold. So I mentioned a spectral algorithm, but note that the spectral algorithm involves computing complex eigenvalues of a asymmetric matrix. So there's no natural SDP relaxation or a SDP hierarchy, which actually achieves the threshold before we start proving lower bounds for it. And so in particular, there's no definition of sum of squares degree yet. And so that's our main result in some sense. So we actually propose an SDP hierarchy. We call it the local statistic hierarchy. It parameterized by two quantities, D and capital D. And it can be solved in n to the little d time. And basically, we show that this hierarchy can solve the detection problem as close to the threshold as you want. So for all stochastic block models at epsilon before case threshold, epsilon above case threshold, there exists some fixed constant d, such that you can solve local statistic 2 comma d SDP hierarchy. SDP relaxation solves the detection problem. Okay, that's our main algorithmic result. And then, of course, as I said, SDPs are robust to edge removals and additions and so on. So immediately the SDP algorithm is also robust. And then finally, we also show a lower bound for this SDP, and a very, admittedly, a very somewhat of a weak lower bound in the following sense. We prove a lower bound for the regular block model, meaning a regular block model is basically the block model that I described, but now you condition on the graph being a regular graph. You sample the graph, and then you throw it away if it's irregular. Okay, so it's still a very natural model. Still, a lot of the complications are still there in this model. It's not trivial to solve this problem, even on this model. And in this, like for regular block models, we show a lower bound. What we show is that below the case threshold, local statistic 2 comma capital D cannot detect for any capital D. So for any constant capital D. So there seems to be two parameters in my local statistic hierarchy for little d and capital D. Think of little d as the degree of the usual SDP, sum of squares SDP. So this is like a degree 2 SDP, and capital D is some complexity of the constraints that we are going to introduce in the SDP. So what we're saying is, if you keep the degree of the SDP 2, but you increase the constraints, and you don't solve below the case threshold, the problem is not.
Can I ask one question? Yeah. So the lower bound for small d, do you know how to get a lower bound for d bigger than 2?
No, we don't know. I don't know. I mean, I don't know. It's actually, in this case, it's even more, it's fairly concrete, because I'll describe the SDP. The SDP will tell you there's only one solution to the SDP. There are not. So really, the problem boils down to proving that SDP solution is positive semidefinite. That's the future work, I guess. Yeah, but really,
also, can you explain the significance of this regularity? Is it just a technical issue, or is it something?
Actually, we first solved the regular thing first before we did the irregular thing case. So I guess what happens in the regular case is that essentially we will talk about non-backtracking walks in a while. Basically all the non-backtracking walks, matrices of non-backtracking walks, are univariate polynomials of the adjacency matrix in a regular graph. Right, and therefore everything boils down to univariate polynomial problem. It's a very nice, actually quite elegant. The regular case is quite elegant because everything is univariate polynomial. So proving that the SDP works is some question about univariate polynomials. Proving a lower bound is some other question about univariate polynomials. It's quite natural and elegant because of that reason. And I mean, technically what's happening is in a regular graph, the A matrix, the adjacency matrix, and the degree matrix D. Degree matrix is just D times identity, so they commute. So all polynomials in A and D are really just univariate polynomials in A. Whereas in an irregular graph, A and D don't commute. So all polynomials in A and D are basically, yeah, just a non-commutative polynomial in A and D. So things get much more complicated because of that.
Okay, thanks.
Right. Okay. So okay. So let's see. What's the right SDP relaxation? So this is so let's try to solve this problem. So we want to write an SDP relaxation for this. So if I look at the original setup, I added more edges within the cluster. I said every edge within a cluster sampled p times 1 plus epsilon, and fewer edges across the cluster. So the most natural algorithm would be, at first shot, would be to try to find a min bisection. Try to find an x that minimizes the number of crossing edges, right? Because there are fewer edges crossing, and you try to find an x that minimizes. And this we know how to write. You know, this is almost quite similar to Gomans-Williamson max cut SDP. Your unit vector for every vertex, and you minimize the number of crossing edges. Okay, so it's pretty much the Gomans-Williamson SDP, and then this SDP actually works if you're quite a little bit far away from the threshold. It works, and in fact, if you make the degree tend to infinity, this SDP is known to work as you approach the threshold. But for a fixed degree, we don't know that it works to the threshold. And really, what is this SDP trying to do? Like, if you think about it, what this SDP is trying to do is to do the following. Really, we had a Bayesian model. Our graph was, we didn't have an optimization problem to begin with. We had an inference problem. We had a graph G, and we had a conditional distribution X given G, which is just given by the Bayes rule, right? We have a Bayes rule. And what we really want to do is to sample from X given G. It's an inference problem. We're not trying to optimize anything at first. We cast it as an optimization problem when we try to write an SDP. Okay, and so by casting it as an optimization problem, what we're really solving is not the problem of sampling X, but it's really something about the max likelihood estimate. So you want to find X that's most probable, right? That's what we are trying to do. And this is a bit problematic because here's somewhat of a surprising fact is that if I just take a random graph and find the min bisection in a random graph, that can actually be better, or I mean, that can have a smaller objective value than the planted bisection in the planted graph. So a min bisection in a random graph, because of fluctuations, there are 2 to the n different bisections. There'll be some which are very small objective value and some will be large. There'll be fluctuation just because there are 2 to n of them. So the smallest bisection in a random graph is actually smaller value than the planted bisection of planted graph. So that's bad. Sorry.
Just a question. We should think of P as a constant or something that depends on n and is very small.
P. Oh, yeah. P is a constant. P is a constant.
Okay.
Yes. P is a constant. Yes. Yeah. So in fact, right. Yes, P is a constant. So and so. In some sense, the issue here is that even if you had an exponential time algorithm that found the best min bisection, we don't know if it correlates with the original planted bisection. I mean, probably does, but we haven't. Nobody has proved it. And furthermore, the following NP thing is false. Suppose I give you the communities and tell you, look, suppose I give you the communities and you check the min bisection value. That test of whether the community is right is actually doesn't have soundness, in the sense that even in a random graph, I can show you a bisection whose value is small. Okay. So somehow the simple SDP is failing, and the reason is basically because of we had an inference problem, and we threw away all the information that we had about the problem, and we only cast it as some min bisection problem. Whereas actually, why did we look at number of crossing edges? It's not the only natural thing. We could have looked at number of paths of length 2 of certain type, or a number of structures of a different type. No one, for the original inference problem, all of these are just as equally, natural and canonical. So, so in fact, we could have looked at a linear combination of this. Why don't we minimize the number of crossing edges plus 2 times the number of crossing paths and 3 times this? So, and in fact, if you look at the sampled graph, if I sample a random graph from the community model, all of these quantities are quite well concentrated. Number of crossing edges is some constant times n with root n deviation. Number of crossing 2 paths is some other constant times n plus root n deviation. So we should use that as our SDP relaxation. So the SDP relaxation says the following. So now we have a graph G given to us. Find an X such that for every local structure, by local structure, I mean a subgraph with D labeled vertices and D minus little d unlabeled vertices. So the number of copies of this labeled subgraph in the SDP solution is equal to the expected number of copies of that in the planted model, and we allow for a little bit of slack. Okay, so that's sort of the main SDP constraint. So, so if we go back to our number of crossing edges, instead of minimizing the number of crossing edges, we'll say the number of crossing edges should be p times 1 minus epsilon n over 4 plus or minus some delta root n, some constant times root n. And then number of crossing 2 paths should be this p squared times 1 minus epsilon whole squared n by 4 plus or minus constant times root n. So things like that. So for every small subgraph structure, we can write down the number of copies of that structure in the graph as a polynomial in X and G. And what we're saying is the pseudo expectation of that polynomial is equal to the expected number of copies in the original model. This is, as you can see, it's clearly inspired by this idea of pseudo calibration from SOS lower bound. I should also mention Hopkins used ideas from pseudo calibration for inference. They used a different SDP, which is somewhat different. I will not get into the details. So this is the local statistic SDP relaxation. Are there any questions on this? I don't know at what point I got cut off.
Could you say again how you said something about it being a polynomial?
Right, because so it's just that the number of any like, let's say I want to count the number of paths. Let's just count the number of crossing edges. What is the number of crossing edges? Well, I have the variable xi, which tells me the label of every vertex. These are the variables xi, and so on every edge, number of crossing edges is 1 is 1 plus xi by 2 times 1 minus xi by 2. That's the indicator that xi is 1, xj is 0. Sum over all the edges. So we want crossing 2 paths, sum over every path. What's the indicator that the one endpoint is 1, the other endpoint is -1? It's 1 plus xi by 2 times 1 minus xj by 2. Sum over. So basically, any labeled subgraph structure, partially labeled subgraph structure, is a polynomial in xi's.
Okay, sure, thanks.
And then that's why you say that its pseudo expectation is equal to the expected number of copies. Yeah. Okay. So let me step ahead. So that's the SDP relaxation, and now I'll get into the proof of why this SDP relaxation should work. If there are no more questions about it. Okay, so let me get into the proof. So what do you want to prove? I want to prove that this SDP works above the case threshold. And basically, by definition, the original communities are actually a solution to the SDP. In fact, that was a key requirement of the SDP that I wanted to write, was that I wanted to write an SDP for which my original communities are a solution to it. That's sort of the most canonical thing. It should be true. And then so it's definitely there's a feasible solution when the graph is drawn from the communities. There's a feasible solution. The question is really, if the graph is a random graph, can we prove that this SDP is infeasible? Okay, how do we prove that? Well, okay, so now to prove that, of course, to prove an SDP is infeasible, we have to exhibit a dual certificate of infeasibility. So I'll show the dual certificate of infeasibility, but before I do that, let me just define something. So these are called non-backtracking walks. So we're going to be talking about walks in graphs, and a backtrack on a walk is when you walk on an edge UV and you immediately retrace your step to U. So you go to U to V and then you retrace back to V, U. That's a backtrack. And a non-backtracking path is a path that never does that. So it never immediately retraces its step back. And, you know, these are actually quite restrictive if you think about it. So if you're in a tree and let's say you start walking away from the root, if you never backtrack, you'll keep going down. You can never turn back, right? So non-backtracking paths from the root will keep going down away from the root. And I want to define this thing called the non-backtracking power of a matrix. So what is a usual matrix power count? If I have a matrix M, and if you look at M to the L, every entry of M to the L is sum over paths of length L of the products of the M values on the path. Now, if I do the same thing, but instead of going over all possible paths of length L, I sum up only over non-backtracking paths of length L. That's my non-backtracking power. So M to the non-backtracking power L of UV, the entry UV of M to the L is sum over all non-backtracking paths of the products of the M values on that. So it's a natural operation that you can define on any matrix M. Okay, so that's fine. So now I'll describe the dual witness. So we have A, which is our adjacency matrix, and we have J, which is let's say the all ones matrix. So let me define heavy vertex. So note that we are working with this model of we are dealing with a graph which is an Edo-Srini graph. An Edo-Srini graph has vertices of all kinds of degrees. There are vertices of degree 0 and also vertices of degree log n. And a heavy vertex is intuitively a vertex with very high degree. More formally, actually, what I want to say is a vertex is heavy if the number of vertices in its neighborhood of radius t is too large. So in a neighborhood of radius t, you expect d to the t neighbors. If you have a average degree d Edo-Srini graph, you should expect d to the t neighbors. And if it's more than d to the t times 1 plus epsilon to the t, I'm going to call it a heavy vertex. For now, let's just
a second. One question. It seems now that the graph is the constant degree graph for this definition, where beforehand you mentioned that P, the probability of an edge, was constant, so I expected a dense graph.
Oh, sorry, I meant constant by n. Oh, yes, sorry.
Oh, you meant constant by n. Okay.
Right. Oh, yes, I'm sorry. Yeah, it's P. Yeah, it's P over n. Yeah, sorry, it's P. P is a constant by n. Yeah.
Okay.
Yes, yeah. It's a constant degree graph. Yes.
Thanks.
Right. So, what is the what's the witness? Well, you take the adjacency matrix, you take out the non-trivial all ones eigenvector. Essentially, there's an eigenvector which is the largest eigenvalue. You just take it out, and then you take this matrix, restrict it to the light vertices. Light vertices are vertices which don't have too many neighbors. Just think of it as too many neighbors for the rest of the talk. And And then you take the Lth non-backtracking power of this matrix for some large constant L. So that's a matrix. I'm going to call it a dual witness. So that's the matrix. I'm going to write it down. Okay. And essentially, the statistic that corresponds to this matrix is going to be our distinguishing statistic. So it's a low degree statistic. It's the X transpose MGX. So intuitively, what you can think of is this statistic as you have a non-backtracking walk of length L, and you somehow force every vertex on the non-backtracking walk to be low degree, although it's not really degree, it's low degree, and you count the correlation of the endpoints. So I look at the correlation on endpoints of non-backtracking walks that only go through low degree vertices. So that's sort of the statistic you're looking at. And the claim is that this statistic is a distinguishing statistic. Essentially, what we show is that if you sample a Erdős-Rinyi graph, then the spectral norm of this matrix is slightly larger than root d to the L. Okay, slightly larger than root d to the L. Because MG is an L-step walk, it's like a non-L-step walk, you should expect an exponent in L always. The key number to remember is square root d. Square root d is like the Keston-Stingham threshold. It comes from the Ks threshold. And what we're saying is you can get arbitrarily close to the Ks threshold in that sense. And so, once you have the spectral norm bound, it immediately tells you that for every SDP solution, this is true, that the value of the statistics is small. And on the other hand, you can show that in a planted graph, this statistic is large. Okay, so that's the basic idea. Okay. All right. So essentially, what it boils down to is proving this somewhat horrible-looking spectral norm bound. It's saying the following thing: if I sample a Erdős-Rinyi graph and I compute A minus d over n, remove all the high degree vertices, and then take this L step non-backtracking walk, then the eigenvalue of this matrix is at most square root d times 1 plus delta to the L. Okay, and for all of these random graph spectral norm bounds, the natural technique is a trace method. So it boils down to the following thing: you would want to bound, instead of bounding the spectral norm of the matrix Mg, you instead bound the expectation of the trace of Mg to the k for some large k. K should be quite large. It should be like some large constant times log n. And once you have a bound on the expected trace of Mg to the k, you will get the theorem immediately. So in some sense, right, so far this is the so now it's in some sense it just becomes this question of how do we calculate this expected trace of Mg to the k for this complicated looking thing. And it's a fairly complicated, involved counting argument, you could say. The analog you should think about is like trying to prove 2 root d minus 1 for random d-regular graphs or things like that. And so in the rest of the talk, I will not try to get into the details of the counting. I'll try to describe the salient features of the counting argument, which sort of should tell us where these numbers square root d, 2 root d minus 1 are coming from. So I hope that's useful. So I'll try to do that.
Can I ask you? So the bound on the norm here looks like square root of d to the L, which would be the degree of the backtracking matrix.
D would be the degree of the Erdős-Rinyi graph, yeah.
So
Average degree of the Erdős.
I guess what I am trying to understand is it was very surprising to hear that in a random graph that doesn't have the communities planted, the bisection could be very small, smaller than in the other case.
Yes, yes.
So why would we expect that here something better is, or?
Yes, right. I think it's something to do with um, the fact that the statistic looks at L-step non-backtracking walks. So I think the fact that it's L-step non-backtracking achieves two things. One is somehow it ignores high degree vertices, because if you're at a high degree vertex and you take an L-step non-backtracking walk, you sort of leave the vertex and you'll never come back to that vertex. For L steps, you're not going to be coming back to that vertex, right? You cannot come back for L steps because you're going to run away from that vertex. So in some sense, doing L step non-backtracking walk normalizes for high degree vertices. It also, I don't understand this very well. It somehow normalizes. It's a better statistic, well-behaved statistic than the number of edges cut for some reason. Maybe it's better concentrated. I'm not, maybe it's better concentrated because you take the L route eventually. I'm not very sure like in how this actually beats that fact.
Okay,
Yeah.
very interesting. Okay, thanks.
Yeah.
But it is related to the fact that algorithms that use non-backtracking walks, as opposed to SDP and non-backtracking in the analysis,
right.
to work before, right? It's at least the same intuition.
Yes, yes, yes. Yeah, it is. Yeah, non-backtracking walk matrices. They come from. I mean, this algorithm works, and actually, non-backtracking walk matrices are fairly natural. Isn't that that's the natural way to define generalization of Ramanujan graphs for irregular graphs, and also um, I mean, all the predictions that I mentioned. The belief propagation based predictions. So some if you try to see where the prediction comes from, the natural object that arises there is the non-backtracking walk matrix. There's some dynamical system, and you look at whether the fixed point of the dynamical system is stable, and the natural object there is the non-backtracking walk matrix and not the original adjacency matrix.
So is the problem the high degree, in the random graph, the problem is the high and low degree vertices? Like if you chose a random deregular graph, would this mean bisection problem not occur?
No, even in a deregular graph, the min bisection problem would occur. So the high degree is one issue of the problem. The other issue is really that somehow, yeah, non-backtracking behaves better than the original adjacency matrix. Actually, you'll be off by a factor of 2 if you use just the adjacency matrix. The correct threshold for a regular graph is square root d minus 1. Instead, your algorithm will work at 2 times square root d minus 1. So, so somehow it'll be, even on a regular graph, you need non-backtracking.
I'm wondering if a simple example of this phenomena is what happens if you are just trying to count not just the number of crossing edges in the bisection, but let's say the number of crossing paths of length 2. If you don't have backtracking, then you will have a factor of the going over an edge and back again.
Right.
You don't want. So you want to somehow count without it. And you do a non-backtracking,
right,
just raising to the power 2 of this non-backtracking
yes,
random walk, you do count the paths that are crossing the cut, but not the edges that are crossing the cut. So
right.
this is aggravated, or I don't know, not aggravated, but improved as you go with longer walks.
Yes, yes, yes. So that's right. That's right. Yeah. And in fact, I hope to show a place where actually this factor 2 goes away. Like if you just use the adjacency matrix, you get 2 times root d minus 1. That's our favorite Ramanujan bound. But if you use non-backtracking, you get root d minus 1, which is the right answer. I'll actually hope to get to that in the trace. some other, I hope to give some intuition over there. So, I mean, so we're going to calculate expected trace. So it's going to be about counting closed walks. So let's just start with the simplest thing. I want to count the expectation of trace of the adjacency matrix to the M in a random deregular graph. Okay, pick a random deregular graph. I want to calculate expected trace of A to the M. Okay. I'm going to make an assumption which is not true, just to give some intuition that I'm going to assume that graph looks like an infinite tree. Okay, so the walk looks like a tree walk. So the actual walk only looks like a tree walk in a tree. So we are actually, what we're counting is the total number of closed walks in a complete graph, right? Closed walks in a complete graph. So let's just count it based by actually encoding the walk. So we're going to walk and we're going to write down bits to sort of remember the walk as we walk. So every time we encounter a new vertex on the walk, I'm just going to write down its name. So, okay, that's going to be log n bits. Okay, that's fine. Okay, then the key thing is I might go back to a vertex that I already saw, right? I already saw this vertex, I'm going back to it. Okay, now, but the key point is all my walks are on the tree. So, which means that on every step is going to be either up or down this tree, right? So if it's up the tree, or it could be up the tree or down the tree, and I'm just going to write down whether it's up the tree or down the tree. That's be 1 bit to say whether it's up or down the tree. It's 1 bit. And if it's up, if I'm going up the tree, I don't need to tell you where to go because there's only one way to go up. In a tree, if you have a root, there's only one way to go up. So I don't need to tell you where to go. But if you're going down, because the tree has degree at most d, there are at most d minus 1 choices for the children. And so if you're going down, I need to tell you which way to go. So that'll be log of d minus 1. So in some sense, the total number of bits I use in this encoding is for every new vertex that I encounter, I need to write down the log n bits, the name. For every time step, I need to tell you whether to go up or down. That will be 1 bit. And every time you walk down, I need to tell you log d minus 1 bits. So, and the key point, the key fact to observe is that the number of down steps is always equal to the number of up steps because you have to go to the root. You start at the root, you walk anywhere you want, you have to go back to the root. So which means the number of up steps is always equal to the number of down steps, which means the number of down steps is half the total number of steps, right? So the number of down steps is half the total number of steps. And so this is essentially gives you some count. And I want to show that this has some of the right answer hidden inside it. Why? Because notice how many bits you're using per step. So per step, I'm telling you whether to go up or down. That's 1 bit. And then if you're going up, I don't tell you anything. But half the time, I need to tell you log d minus 1 bits. So per step, I'm on average spending 1 plus half log d minus 1 bits. So it's log of 2 root d minus 1 bits per step. So that's where somehow you see the 2 root d minus 1 pop up. And that's really the Ramanujan bound answer, right? Of course, this is such a caricature of an argument because I assume that the graph is an infinite tree, right? It's not an infinite tree, but that's sort of where that number 2 root d minus 1 is going to show up, and that's what's happening. Okay. All right. Okay. So now let's see what happens now that we have non-backtracking hops. So again, I'm going to sample a random deregular graph, and I'm interested in this quantity, which is trace of a non-backtracking power L whole to the M. So these are walks of length LM, which consist of non-backtracking segments of length L. So there's a non-backtracking segment of length L followed by another non-backtracking segment of length L M times, and I need to come back to my root. So, and I'm interested in the trace of this. again, we need to count such walks. And again, let's assume that the graph is infinite tree, locally infinite tree. Okay. So I just reproduced the calculation that I had in the previous slide without any change. Every new vertex I encode with log n bits. Every time I need to go up or down, so it's 1 bit. And every time I go down, I need to pay log d minus 1 bit. So far, I just copied it back. The key point is that this is wasteful. I don't need to tell you whether to go up or down every time, because note that you have non-backtracking segments of length L. In a non-backtracking segment of length L, you don't change direction. If you're going down the tree, you keep going down the tree. If you're going up the tree, you might go up for a while and then turn and go down. But you cannot do more than one change. So essentially, there are at most 2 changes of direction in every L steps. So effectively, instead of telling you 1 bit every step, I have to sort of tell you order log L over L bits. I think order 1 over L is too cheap. Basically, there are only 2 changes of direction. I need to tell you, where those 2 are in L steps, every L steps. So it's like log L bits in every L step. So basically, it's negligible as L goes to infinity. So what's happening is per step, the number of bits I'm encoding is like order 1 over L plus, that's negligible, plus half log d minus 1, which is basically whenever I go down, I need to say which of the children, and that's half log d minus 1. So I get log root d minus 1. So you get a bound which looks like square root d minus 1 instead of 2 times square root d minus 1. So you can see that somehow using a to the L, looking at spectrum of a non-backtracking walk L gives you this factor 2 out, and yeah, as L goes to infinity. Okay, so that's really the somehow place where like some of these numbers, root d minus 1, 2 root d minus 1 show up. And now if you look at, okay, so I did all this calculation in a random deregular graph. Now instead, if I try to do this in an Erdos-Renyi graph, okay, in an Erdos-Renyi graph, of course, there'll be vertices of very high degree, right? There'll be vertex of degree log n. So which means that if you had to encode all of its children, you take log of log n, you get log n bits. That's much larger than log d. So we don't want to, we would never want to lose that much per step. We'd want to lose essentially log d over 2 per step. And the idea here is just the following. By the way I constructed the matrix, my walk only goes through light vertices that have at most d to the t neighbors at distance t. So if you have d to the t neighbors at distance t, that's effectively saying that I can tell you t steps from this vertex at an average cost of log d per vertex. So a t step neighborhood has d to the t, roughly d to the t neighbors. So it takes log d bits on average to encode 1 step on this t step walk. So what you can do is if you're going to walk up and down this tree, whenever you're walking down, there'll be like a stretch of walking down. There'll be an L step stretch of walking down. Break it up into pieces of t steps and encode the t steps at once. Meaning, starting from this vertex, I'll tell you the name of the vertex at distance t from it, which you have to reach in t steps. And that takes log of d to the t, which is t log d, which is log d per step. So that sort of takes care of this issue of irregularity. But really the big issue, is really the tree-like assumption, right? So this is a major issue because if, if whatever I said so far was argument, it would be very easy to prove that in a random deregular graph, all the eigenvalues are 2 root d minus 1. but it's not easy, right? It's quite difficult and tricky. And the reason it's tricky is because actually it's not tree-like. The graph is not tree-like, especially because we are going to be looking at walks of like 1,000 times log n length. Because we are applying the trace method, we're looking at walks of length 1,000 times log n. So there will be necessarily many cycles in that system, and your walk will go through many of them. And I don't want to get into many details here, but what breaks is once you have a cycle, the following is no longer true. The number of down steps is not equal to the number of up steps. In fact, right, because you can in a cycle, right? Yeah. So I won't get into too many details here, but I'll just say that the general idea is fairly natural and simple. We sort of take the walk, break it up into segments, each of which looks like a closed tree-like walk. So we sort of, what we do is we take the walk, which might have cycles, but essentially it has cycles, but it's not going to be too complicated because the girth is large for these graphs. So how it looked like is, it looked like maybe there's one big cycle or a few big cycles, and you have many closed tree-like walks stuck to it. So essentially we break the walks by taking out all closed tree-like walks from it. You could say you could break the walk into closed tree-like walks. That's sort of the idea. I will not get into the details of the counting, but there are a couple of interesting, maybe one or two interesting ideas in there, but I'm not getting here. And before I go further, finally, I want to talk about robustness. What do we know about robustness? Well, if I change the graph by a small number of edges, I don't change the subgraph counts by much. Basically, robustness comes from the fact that these statistics are robust. So the SDP remains feasible. The fact that the SDP is robust just comes from the fact that the statistics are robust. And just to summarize, what we have is we have a SDP hierarchy. It's a local statistic SDP hierarchy. And the key point is it's a natural way to encode prior information from about the input. You have a distribution on the prior you have prior distribution on the input. You can encode information about that into the SDP. It's a natural way to encode, and you can use it for essentially a large family of these Bayesian inference problems. It need not be on graphs. It could be continuous problems. But basically, the idea is just that some of the low degree statistics, as inferred by your SDP, should match the low degree statistics of the prior distribution. And this gives you a kind of a knob which you can turn. You can make the SDP more and more complicated, and it will be less and less robust, but it will be more and more accurate. So there's a knob which you can turn to change the algorithm from being more robust to less robust, and so on. And so the future work is really, okay, can we use this local statistic SDP to demonstrate precise phase transitions for these problems? And so in particular, the key question that's open for community detection itself is, can you show that this SDP hierarchy, even at, let's say, root n rounds, doesn't solve the distinguishing problem below the threshold? And then, of course, there's a question of optimal recovery of clusters. We still don't have efficient algorithms that recover all the clusters optimally. And maybe this SGP's rounding could give a way towards doing that. And finally, I want to just sort of give you a much easier question, which is surprisingly, I don't know, there hasn't been any work on it. But it's sort of this question of, okay, this prediction says above the threshold, the problem is solvable in polynomial time. And below the threshold, it's hard. Okay, but how hard is it? Is it in NP or is it even higher? So here's an NP version of the problem. So I give you the graph, and I also give you the communities. So I give you the graph and the communities, and I ask you to verify it. So it's an NP version of the problem. But of course, I want you to solve it below the case threshold, just below the case threshold. and figure out how far below the case threshold you can solve this problem. What you need to do is to verify that I'm telling you the truth. That if I gave you, if it's a community model and these are the true communities and that's the real graph, you should accept. If it's a random graph, no matter which communities I pick, you should reject. Okay, so it's really verifying that these communities generate this graph. That's really the very basic question, yeah, we don't know an algorithm for this, and it'd be interesting to figure out if the complexity of this problem has something more interesting happens beyond P, like whether NP does it stay in NP throughout the region or not. I think I'll stop for questions here.
Great, thank you very much. So now any questions?
I have one as usual. Yeah. I heard many talks about the stochastic block model, and I often wondered, even in this robust version where you let a few edges change, why is it so popular? I mean, does it capture anything in real life networks, in Facebook networks, in you know, whatever networks that are out there where you really want to know communities? Is it relevant?
Yeah, I don't know if it's actually relevant in that sense. I mean, it's hard to know, right? It's hard to know. I mean, I guess, but I think, you know, if you think about Bayesian problems, right, inference problems, it's a very, very simple inference problem. It's a bit like max cut. Right? Max cut is almost never there in any real life situation, but it's a very natural optimization problem to study to understand optimization, combinatorial optimization. And I feel like this is a very simple, the simplest problem, Bayesian inference problem, high dimensional inference problem. It's combinatorial, it's simple, that you can study the algorithmic techniques and limits and so on there. In a real inference problem, of course, you have a general graphical model and you need to infer these things, and belief propagation is used in real inference, in graphical models and so on. And of course, over there, you know, every vertex has a more complicated label, and then there's complicated information between how the two interact. But this is like the max cut of inference, I would say. And it's nice that, you know, it has this precise predictions and thresholds and things like that. Yeah, and I think that's right. Yeah, yeah.
And as you said, it's a nice average case, simple average case problem.
Yes, actually, that's true. It's surprising that it would be somewhat surprising if this problem is actually hard. I mean, it is probably hard, but it's kind of a very simple to generate average case hard problem. And yeah, I mean, I've spoken a little bit to some cryptographers, and they're usually surprised that this problem is hard. Right? You can just sample, for example, another problem which is a special case of this is coloring, right? You sample a deregular graph conditioned on it being colorable by less than square root D colors. And that's supposed to be NP. It's supposed to be indistinguishable, computationally indistinguishable from a random deregular graph. A random deregular graph with root D minus 1 colors is computationally indistinguishable from random deregular graph. And that's the claim, at least. Yeah, we don't.
Conjecture, yeah.
Yeah.
There were attempts to use blunted click in cryptography, so.
There's also the dense subgraph thing, right? Yeah.
Can I go back to that technical thing? So in this random graph, after you've given me the mean bisection, so now I have conjectured communities, what will look different from graph sampled from the two community thing?
Right. It will probably look different. Yeah. And I don't know, and like I don't have a good intuition in what sense they'll look different. I think maybe the cut will be getting high value because of a small number of choices, very good choices.
Choices of what?
Like when you pick a min bisection, you're picking which side to go. For example, the optimal bisection will be locally optimal, right? Like meaning, given the neighbors, it will be on the perfect, to the best possible side. But this one, the planted one, won't be locally optimal, right? Somehow it will be clear, I think, if you look at the optimal bisection, that it made just the right choice at every local neighborhood to get the largest possible value.
But it's not like you can, supposedly, if I look at all the path statistics, they should also tell me that this mean bisection is not good, but it's not clear where or how they will fail or how they will distinguish.
I think maybe just that, maybe it's just the fact that if you, I don't have a good sense of this. I mean, maybe just the fact that if you look at, like, it's easy to sort of do the best possible thing when you're just counting edges. Like given the neighbors, you want to do the best possible thing. And doing the best possible thing gives you an advantage of 1 over root d or something, right? Because you expect half plus 1 over root d to be one color, half minus 1 over root d to be another color. And somehow if you did the wrong thing, you lose a root d, right? But if you are looking at things which are L steps away, the choice, like your own choice, changing just your own choice doesn't change the eventual outcome by much, because the bias if at L steps away is like 1 over d to the L over 2. So in some sense, if I change my, like a single vertex changing its own color doesn't pay much. It only pays like 1 over d to the L over 2, maybe, instead of, So maybe, right, there's no way to make few good choices to improve your cut value. You have to be globally good. Yeah. But right, I guess we never tried to come up with an SDP. I mean, this was actually not the first SDP I tried. This was like the second or third SDP I tried. I tried to first try to encode belief propagation in the language of SDPs and so on. Those things failed, but never tried to actually break the optimal min bisection in a random graph thing. Like in the sense that and the fact that this NP question is still, I mean, it's non-trivial, is actually, I find that quite interesting. That just that if I give you the communities and the graph, it's still, we don't know how to check it. Maybe in Sharpie we could just apply base rule or something, but
Thanks. Any more questions? Okay, well, thanks for a very interesting talk, despite all the difficulties.